Hello students, I hope you are doing beautiful mathematics. In this video, we will start with the revision of number theory for mathematical Olympiads such as IOQM, American Math Competition, and ISI-CMI Entrances. So in this video, we will talk about 5 concepts: the greatest integer function, the division algorithm, primes and composites, GCD and LCM, x to the power n minus 1, the factorization of it, and I will discuss some of the strategies that has been proved very useful, very effective in these type of non-routine mathematics competitions. Let's start with the greatest integer function, the GIF, greatest integer function. So many of you are familiar with this. I will just give you a quick example. Let's say if you have 2.3 and you want to apply the greatest integer function to it, usually denoted by square brackets. It is the greatest integer smaller than 2.3, that is 2. The greatest integer smaller than the number itself. Similarly, if you have negative 3.1, the greatest integer function, if you apply to negative 3.1, you will get negative 4. Here is a key strategy to attack problems involving greatest integer function. Suppose you have a number x and you take the greatest integer function of it. We will call it I for integers, and there is a fractional part of it which is known as curly bracket x, denoted by curly bracket x. This is sometimes denoted by f for fractional part. Every number can be divided into I and f. If you have a function, if you have a problem involving greatest integer function, then it is always useful to replace x or whatever the variable is by I and f. So for example, if I have the number 2.3, then I would be 2 and f would be 0.3. Remember, f is always between 0 and 1. 0 is less than equal to f is less than equal to 1. Similarly, if you have minus 3.1, then I would be negative 4. Notice that the I part can be negative. And this is the greatest integer function of 3.4, negative 3.1. Plus, this is f is 0.9. So notice that negative 4 plus 0.9 is indeed negative 3.1. Always, this is a sort of the standard procedure, standard way to attack these problems. You split the number x into I and f, and then you start solving the problem. Okay, so let me write it down. X is always equal to I plus f. You replace x by that. Keep in mind that f, the fractional part, is always between 0 and 1. It can't be 1. It's a little bit less. It should be less than 1. I could be negative or positive or 0. Okay, so that's the first concept, the greatest integer function. The second concept is division algorithm. It's equally important. Let me write it down. Division algorithm. It is a theorem in elementary number theory that if you have two integers a and b, if a is an integer, b is an integer, then there are integers, there exists. This is this sign. The reverse E sign means there exists unique numbers. Multiplication, this exclamation mark means unique numbers q and r such that A is equal to BQ plus R. really, Q should be the quotient and R should be the remainder. That's how you should think about it. That's exactly what they are. R, by the way, the value of R should be between 0 and the other number B. B is the divisor in this particular case. Of course, you can switch the positions of B and A. I mean, you will get a different set of quotient and remainder. So, the remainder should be obviously less than the divisor, which is in this case B, and 0 is less than equal to the remainder. If the remainder is equal to 0, then we say that A is divisible by B. Now, you may think that this is kind of trivial because obviously we know this is how the division works. The dividend is equal to the divisor times quotient plus the remainder. But you will be amazed how effective this simple symbolic representation is in solving interesting problems. One thing that people often do is they use division algorithm to categorize numbers. For example, this is an extremely useful use case. Let's say you have the number 3. On the basis of the number 3, you can categorize all integers in 3 categories. One, those are divisible by 3. One which produces remainder 1 when divided by 3. And the third one which produces remainder 2 when divided by 3. 3k, we write it like this. 3k plus 0. 0 is the remainder. K is the quotient. Doesn't matter what quotient it is. We are just interested in the structure of the number. 3k plus 1 and 3k plus 2. Obviously, if you divide any number by 3, the only possible remainders are 0, 1 and 2. So all integers will fall into one of these 3 categories. So how this is useful? Let me quickly show you a simple application. If you square a number, of course you get perfect squares. So let me square each of them. Squaring 3k, I'll get 9k square, which is essentially 3 times 3k square. So a multiple of 3. If I square a multiple of 3, I will get a multiple of 3. No problem with that. Let's square the next one, 3k plus 1 whole square. It is 9k square plus 6k plus 1. But that is 3 times 3k square plus 2k plus 1. So it is of the form 3 times something plus 1. So this produces remainder 1 when divided by 3. So a number which produces remainder 1 when divided by 3, if we square such a number, that also produces remainder 1 when divided by 3. Think about it. Okay? So that's the second part. Nothing surprising has happened yet. But let's come to the third part. 3k plus 2 whole square. That is 9k square plus 12k plus 4. Now notice what we have. 9k square plus 12k plus 3 plus 1. Just I wrote the 4 as 3 plus 1. Now I have 3 times 3k square plus 4k plus 1 plus 1. So 3 times something plus 1. 3 times something plus 1. That means this number is also producing a remainder of 1 when divided by 3. This is new information in the sense we learn something beautiful about square numbers. What are square numbers? Perfect squares. 1, 4, 9, 16, 25. These are called perfect squares. What do we learn about them? We learn that they are either divisible by 3 or they are always producing remainders 1 when divided by 3. A square number cannot produce remainder 2 when divided by 3. This is a theorem in some sense, right? So you used division algorithm to learn something new about square numbers. This is a very simple but effective way to see how division algorithm is useful in solving theorems and problems in number theory. Okay, let's go to the third idea. The third idea here was primes and composites. Of course, most of you know about primes and composite numbers, but let me quickly redefine it. So, a prime number is a number which has exactly 2 distinct divisors. A number is prime if it has 2 distinct divisors. So 1 is not a prime number and 2 is a prime number because it has 2 distinct divisors, 1 and 2. 3 is a prime number because it has 2 distinct divisors, 1 and 3. 4 is not a prime number because it has 3 distinct divisors. So it is called a composite number. A composite number. There are many beautiful theorems related to prime numbers and composite numbers that can be used as practice problems. One of them that we discuss in our Math Olympiad program is like this. If you have a number n to the power 4 plus 4 to the power n, this number is always composite except for n equals to 1. So if I plug in n equals to 1, I will have 1 to the power 4 plus 4 to the power n. This is 5. This is a prime number. But anything above that, if you plug in n equals to 2, if you plug in n equals to 3, if you plug in n equals to 4, it will not be a prime number anymore. It will always be a composite number. This can be proved using the so-called Sophie-Germain identity. We will talk about it in the algebra revision sessions, but you can also give it a try. It's a very famous problem. You can try to prove it on your own using whatever little algebra that you already know. One fun thing about the solution of this problem is that you have to also use the division algorithm. This is quite interesting. You can give it a try. Primes and composite numbers are, in some sense, the building blocks of all elementary number theory. You take a big number and, philosophically speaking, you would want to break it down into small pieces. You want to write the big number as product of simple pieces, small numbers. So for example, if you have a big number, let's say 48, you would like to do something called a prime factorization, which is 2 times 2 times 2 times 2 times 3. Why do you want to do it? Well, one way to simplify hard things is to break it down into small things. This is almost philosophical. You break down a large big thing into smaller pieces, and then all of a sudden the big thing looks more understandable. So in a lot of problems in elementary number theory, one of the important steps is to do a prime factorization. Okay, let's talk about the next idea. The next idea is GCD and LCM. And finally, we have x to the power n minus 1. Let's discuss these two things quickly. So x to the power What is GCD and what is LCM? Of course, you already know about these things from middle school. GCD is the greatest common divisor. That means if you have two numbers, let's say 6 and 9, then the greatest common divisors of these two numbers is 3. 3 is the GCD of them. And what is the LCM? LCM is the lowest common multiple. Lowest common multiple. So say if you have 6 and 9, two numbers, the lowest common multiple of them is 18. 18 is the smallest number. 18 is the smallest number that is divisible by both 6 and 9. It's awesome. So here is a little question. Notice that 6 times 9 is 54. And notice that the GCD times the LCM is also 54. Is this an accident or will it always happen? Think about it. It's a very simple question. If you have not seen it before, it gives you an opportunity to think. GCD and LCM are extensively used in creating interesting problems in elementary number theory. Finally, for this first revision session, I want to talk about x to the power n minus 1. This is a very important expression in elementary number theory as well as in algebra. X to the power n minus 1 has a very important factorization that is used in many problems. Let's understand this factorization with simpler examples. X square minus 1 when n is equals to 2 is simply x minus 1 times x plus 1. No problem. What about n equals to 3? X cubed minus 1 is x minus 1 x square plus x plus 1. We see a pattern. The pattern will follow, and in fact x to the power n minus 1 will be x minus 1 times x to the power n minus 1 plus x to the power n minus 2 plus x to the power n minus 3 plus x plus 1. Believe you me, this is one of the most important factorizations that you will see in elementary algebra and elementary number theory. Think about a problem that I will give you next. Here is a challenge question. 1 plus x square up to x to the power n minus 1 is prime if n is prime, or rather implies n is a prime number. If this thing 1 plus x square up to x to the power n minus 1, if this quantity is a prime number for some value of x, then it would imply that n is a prime number. It involves factorization, x to the power n minus 1 minus 1, x to the power n minus 1, this factorization. It involves the idea of prime numbers and composite numbers. A lot of things are involved in this problem. It's a pretty challenging problem. Think about it, okay? Thank you for watching this video. This was the first revision session. If you liked it, then please comment in the comment section with your ideas. I will see you in the next one where we'll come back with the next revision session. If you are a student of Cheenta, make sure to continue attending all the problem solving classes as well as the recovery classes. That's how we personalize the experience. Ask for recovery classes to your personal mentors in your WhatsApp groups if you are stuck with a problem or if you need help with some specific concept. And finally, take the mock tests. It's extremely important that we do. One of the reasons Cheenta students do so well in Mathematical Olympiads. Last year we had 10 out of 78 INMO awardees were from Cheenta. So the reason we do so well is because we are super focused on this entire beautiful problem solving process. I hope you will be focused as well. Thank you for watching the video. Take care. I'll see you in the next one.